corre por Silvia Franceschi, viene de la Free University of Bolzano, Italia, y nos va a hablar de herramientas espaciales para la evaluación de riesgos de los residuos leñosos, inundaciones en gvSIG. La ponencia será en inglés.
Okay, it works. Okay. So, I'm Silvia Franceschi. Thank you for coming to my presentation. I am a PhD student of the University of Bolzano, but I am basically an environmental engineer specialized in hydrology and hydraulic and geomorphology. I'm also a co-founder of Hydrologists, which is member of the gvSIG association. In this presentation, we will talk about the wood in rivers. So let's introduce the problem. So in mountainous region, and in particular in the Alps, the basins have been impacted by humans since ancient times. And since the First World War, the forests were regularly and heavily harvested, mainly for timber, firewood production, and for pasture, livestock, and agriculture. But in the last century, with the decline of the rural and forest economy and the depopulation of urban upland area, the forest became old. And so we have the increased presence of shrub, trees, and crops. Just to give you an idea, between the 1830 and the 2000, the average increase of woodland in Switzerland has been more than 20%. The vegetation influences all the water cycle, starting from runoff production, evapotranspiration, erosion, transport, and deposition of sediment and woods in streams. The presence of vegetation on the banks has two main aspects. The first aspect is the ecological aspect, because biodiversity, because vegetation influences the biodiversity, and so the ecological, the local ecological aspect of the rivers. But on the other side, there is also the hazard, the problems related to the vegetation, because vegetation is dangerous on the riverbank because it can be recruited from the flow during a flooding event and so increase the magnitude of this event. So we need tools, we need to balance the ecological aspect and the risk and the hazard aspect. And we need tools to give information, to give to the decision makers and help to take information. So we decided based on all this, we decided to develop GIS tools for predicting the magnitudes of large wood transport during flooding events at any given section within a river basin. We consider only two main processes related to woody debris. The large wood recruitment from hill-slope and for bank erosion, and the large wood transportation along the network. Basically, the area, what we calculate for the large wood recruitment is the area that provides large wood. This area is calculated as the sum of the area becoming from the bank erosion and the area becoming from unstable and connected area to fluvial network. We need to know the distribution of the vegetation on the terrain, and the possibility to understand the volume of vegetation and its characteristic is derived from, can be calculated using two different models. A simplified module that uses a canopy height model and a semi-empirical model of the forest stand, or an approach single tree. So we extract a single tree, each single tree is from the LiDAR data and give information of position, height, and diameter of these trees. Connecting together the area that provides the large wood with the vegetation present in this area, we can evaluate the volume and dimension of the available large wood. And this is for the large wood recruitment process. And then for the other process, the large wood propagation, we need to understand the hydraulic parameters of the river. So we apply a 1D hydraulic model to evaluate the velocity and the water depth, and we extract the section directly from the digital terrain model, correcting the section where there are structures like bridges and dams. Propagation and landwood recruitment will join, and finally we can highlight or localize the critical sections on the river and the amount of large wood volume in each section accumulated in this section. This is an example. This is, for example, the list of input and outputs of the model. As you can see here, we need many DTM-derived geomorphology results like the flow direction, the total contributing areas, the Schultz model, and then we need some other input like the Banful area, the superficial geology, the digital surface model, or the digital or the field, the forest stand volume, and also hydraulic input, discharge, presence of bridges and dams, and also if possible the single trees. The output are the clogging sections and the volume of the deposit at each section. We developed a step-by-step procedure, and we split all the model in different sub-modules, starting from the pre-processing of the data, then evaluation of the attributes for extracting the contributing area, and the recruitment and propagation process in detail. Let's see now some of these tools. For example, a very important step is the network attribute extraction. We need to know the hierarchical distribution of the network, so we need an enumeration of the network. In this case, we follow the Pfaffstetter enumeration, but we developed a tool connected to this one in the JGRASS tool library that makes the enumeration of the network also following Strahler and ACK conventions. And then we need to understand where the flows goes. So we need to have the channel digitalized from upstream to downstream. All this information are extracted from the geomorphological analysis of digital terrain model with some of the tools already developed in the JGRASS tool library. And in particular, we need the layer of the network, the map of flow direction, and total contributing area. As you can see here, this is the graphical interface of the model of the attribute extraction, and these are the result of a very small, very simple network of the enumeration of Strahler, ACK, and Pfaffstetter. So I told you that the area providing large wood becomes from two different processes. The first one is the bank erosion. To know which is the bank erosion, we have to know which is the bankful position. The bankful width corresponds to the stage at which the water overflows the natural banks, and in general it is related to a flow event that recurs every 1 or 2 years. The model requires in input the polygon with the extension of the bankful area that can be created used by a field survey or remote sensing images, and extract the bankful width in each section. Since the data of the network and the data related to the polygon of the bankful have different origin, we have to face also some tricks about the position of the network, because not always the network was inside the polygon, but there are many cases where the network was outside or tangent the polygon of the bankful width. So we had to relate these two different data, and so in the graphical interface you can see here that we request some other parameters just to face this problem. And this is an example of the extraction of the bankful width, and this is these are the sections with the visualized with the attribute bankful width. So another important thing for propagation of wood are the bridges. Usually bridges are the most problematic sections because they tend to clog. So we give the possibility to the user to directly insert the width of the structures, and we maintain this width where there is a structure like a bridge or a dam. There is no possibility for erosion, so no widening is allowed in that part. The bank erosion is then calculated using following a power law of the unit stream power, that it is an hydraulic index to define the power of the flow, and it is proportional to the discharge and to the local slope. As we already told, that the widening is avoided for the section where there are the structures or where there is rock, if the user provides a shapefile with the geology. This is an example. The bankful section are those in magenta, and the widening section, the possibility of erosion is the polygon in cyano. All this information related to the width are stored as attributes to the section layer. The second mechanism for recruiting the hill slope is from hill slopes. For recruiting large wood is from hill slope. We decided that the only process that recruit large wood from hill slope is from shallow landslide on connected areas to the channels. So we can evaluate, we have to evaluate the amount of wood on the unstable and connected areas. So the presence of vegetation is evaluated in one of the two models, using the canopy height model or the total stand volume, or using an approach single tree, where the position of each single tree is extracted from the digital terrain model, from the canopy height model, or from the point cloud. And for each of these three, the position and the height is extracted. Like in this case, we did an extraction on the canopy height model, and each of these points correspond to an extracted tree, and the attribute is, as attribute, we have the height of the tree. Then we have to evaluate where are these areas, which area contribute. The areas are the unstable and connected area. What does it mean? Unstable are those areas that are not stable following a stability model. We choose to use shell stability model. And connectivity is given using this other geomorphology algorithm, that is the downslope connectivity model, that is a sort of distance to network from each point of the hill slope, we calculate the distance to the network, but we weight this distance considering the stability of the cells. So basically, the unstable cells are more connected to the network because they can move easily than the stable cells. Then we divided all the area in subbasing corresponding to each of the network sections. In this case, we can highlight the unstable and connected areas. For example, this is an example. This map is the map of the connection. As you can see, it is not definitely a distance from the network because there are this kind of more connectivity is in yellow and less connectivity is in green. It is because the stability of the cells, the areas, is considered for the connection. And this is these are the subbasins for each section. And connecting those two things, presence of vegetation and unstable connected areas, we can evaluate the contribute of large wood from hill slope to each section. And in this case, this is the result. As you can see here, all the red points are all the trees, but only the trees that are here in a green triangle reach the network. And the result, here you can see it much better. And the result is here, where we highlight the section where there is the most recruitment from hill slope and bank erosion. So bigger sections are those where there is much contribute from the hill slopes. So this is the contribute in each section derived from bank erosion and from hill slope stability. Then we have to propagate this contribution downstream and understand if there are critical sections for flowing with this large wood. So large wood is routed downstream using simple Boolean transport conditions based on the ratio between the length of the log and the width of the sections and between the diameter of the logs and the water depth. These parameters, width of the section and water depth, are evaluated using the one-dimensional hydraulic model using as input the peak discharge. So we can highlight the critical section for the transit of large wood in the given stream network. And this is an example of critical sections. And as you can see here, we insert all the parameters of this critical evaluation as attribute in the attribute table of the section. And here is an extraction of the critical section on the most wider area. As you can see, critical sections are more present, luckily, in the head of the watershed. This is because here we have the smallest sections, the width is very limited, and we have big trees. So the trees tend to store there and not move. So this is what we developed until now. We have to finish some stuff, so our future plan is to try to use the section not directly extracted from DTM, but sections measured from a field survey, a detailed field survey. So it will be more detailed. And then we did almost everything, but it is not finished, to run the model automatically on a wall basin, so automatically connecting the runs on different streams, knowing the position of the streams using the Pfafferter enumeration and proceeding from upstream to downstream automatically without the manual simulation by the user. So this is all. So thank you for your attention and thank you for coming.